Welcome back to another episode of Calculus. In this one, we're actually going to be looking at two different sections. Sections 2 and 3 are very closely related. Section 2 is on differential equations, and Section 3 is on slope fields, which is just the graph of a differential equation. So we're going to look at both of them right now. A slope field, by the way, is what you can see in the background of this title page. So let's start out with differential equations. A differential equation is going to be something of the form dy over dx equals something. It may have x's, it may have y's, it may have both. In this case, we have one that has both. One of the things that we're going to be doing, and one of these big topics, that's what section 2 is all about. We actually saw a little bit of it in section 1 as well, but we're going to be solving differential equations. There are a few different steps. The first step is you have to separate the variables. That is the number one thing. On the AP test, there are always differential equations. They're usually worth 5 to 6 points or so. If you do not separate the variables, you get 0 points. Like, there is nothing right that you can do after not separating the variables. So to separate them, we need to get all the y's to one side, that includes the dy, all the x's to the other side. It may involve factoring before doing that, and then you're going to divide to move them. In this case, we can just divide the y and multiply the dx to get 1 over y dy equals x dx. And now we can take the antiderivative of both sides now that they're separated. So antiderivative of 1 over y dy, 1 over something is going to be natural log of something. So we're going to have natural log of y. Whenever you get natural log, you want to have the absolute values because whatever's inside the natural log is going to be positive, or it needs to be positive. Now we're going to lose the absolute values here in a step or so because we'll see that this will always be positive anyway, so they really don't generally make all that much of a difference here, but it's a good practice to be in to have those. So we have natural log y equals the antiderivative of x is going to be 1/2 x squared plus c. That would get us 2 or 3 more of those 5 or 6 points that I was talking about. There's usually 1 point for the antiderivatives. Sometimes it's 1 point for both together. Sometimes it's 1 point for each separately. And there's usually 1 point for the plus c. If you forget the plus c, you can't score any more points on this problem after that step. But having plus c is an important piece. Now we will usually solve for y. There are certain times if we have like a circle or something, we'll see that later. We don't usually solve for y. We have other equations for that. But generally speaking, we like having y equals something. So we'll solve for y. To get rid of natural log, we need to go e to the power of the other side, which will give us the absolute value of y, but I'm going to leave off the absolute values, and we'll talk about that in a second, equals e to the 1/2 x squared plus c. Notice those are all in the exponents. We can simplify, and so we don't need the absolute value anymore because e to the power is going to be positive. It can't be negative. It's always going to be positive. So the absolute values are not needed. we can simplify this side with the e to the 1/2 x squared plus c, because when we are adding exponents, that means we're multiplying two things, right? X squared times x cubed equals x to the 5th. We add the exponents. So here, y equals e to the 1/2 x squared times e to the c, where c is that unknown constant. What is e to an unknown constant? It's another unknown constant, so we don't need e to the c. We could just write it as y equals c e to the 1/2 x squared. Notice this c that we just had is not the same as the c up top. This new c is e to the c. It's still an unknown constant. Some places you would have, maybe this is c1 instead of just regular c, just to signify that that difference is there. We know the difference is there. We can keep it like this. If you are doing a problem next to a friend, they may have different answers and different steps along the way, but you should still get out to the same thing at the end. And that's something that we'll see in just a second. But this right here is what is called the general solution. It's the general solution. That has a plus c still in it. And so it means it could be a lot of things, but it gets us a shape. In order to find the other piece, which is called a particular solution, which gets rid of that c, we need another piece of information. We need what's called an initial condition. A point, any point on the graph will tell us which graph it's going to be. And so when it's asking for that, it'll give us an initial condition. Here we have y of 0 equals 2. That means when x equals 0, y equals 2. We could plug this in anywhere after the integration. I wouldn't plug it in up here where we still have a natural log. That's going to be obnoxious because we'll have natural log of 2. We could plug it in down in the next step, but I'd wait till it gets a little bit simpler. The y equals the e times e, it's still like we'd get e to the c equals something. I'd just plug it right in to this one that we have at the end. We'll go 2 equals c e to the 1/2 0 squared. 1/2 0 squared is just 0. E to the 0 is 1. It is not 0. Common mistake. E to the 0 is 1 times c. We get 2 equals c. And then we can plug that back into that equation to get y equals 2 e to the 1/2 x squared. And this is what's called a specific or a particular solution. Now, this is where if you were working next to a friend, assuming that you have a friend, if they plugged it in earlier where the c was different, they might get a different number for c. They wouldn't get 2. They'd get, in this case, the natural log of 2. So that when they ended up going e to their c, it would still come out as 2 times e to the 1/2 x squared. So knowing that is helpful. Sometimes it is more useful to be plugging it in earlier on in the problem. You don't have to wait till the end. Sometimes it's easier to wait to the end. It's just any time after the integration, you can plug it in. And so if we're looking back at the points, we had 1 point for separation of variables. we had 1 or 2 points for the antiderivatives, generally 1 point for the plus c. We get 1 point for plugging in the initial conditions. So that would be 1 point right there for plugging it in. And then 1 point for the answer. Sometimes it's general solution, sometimes particular solution, but 1 point for that. So out of the 5 or 6 points, you get all but 2 of them right up there. Easy points to get if you have any idea what you're doing. So that's differential equations and how to solve them. How to graph them gets us into slope fields. And so we can make slope fields. Now we've seen a slope field that's really big. We're not going to be making slope fields quite that big. It's very, very time consuming. We will make some smaller slope fields though. So if we have something like dy over dx equals xy, and then we'll have a graph where we just have to put a slope on each of these dots. We're going to plug in the points to figure out what the slope is. Remember, dy over dx is the slope. And then we're going to make a little line segment with the right slope. So first of all, when x equals 0, we get 0 divided by something. It's going to have a slope of 0. That's going to be flat. So when x equals 0, as long as y doesn't equal 0, it's going to be flat. So we'll have a little flat line, little flat line, little flat line, little flat line. When y equals 0, it's going to be vertical because we'll have something over 0, which is undefined for a slope that's vertical. So we'd have little vertical, little vertical, little vertical, 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 vertical. At 0, 0, there's nothing. Like it's 0 over 0. We just don't even touch that. And so now we can plug in some points. When x and y are equal, x divided by y will equal 1. So we can make a little slope of 1 when x and y are equal. When x and y are equal but opposite signs, it'll be negative 1. And then we can plug in some of those extra points. We have x equals 1, y equals 2 is going to be 1/2. So that's going to be up 1 over 2. It's going to be about in that range. Over 2 up 1, that'll be 2 over 1. So that'll be a slope of 2, so that's steeper. 3 over 1 is steeper still. 3 over 2 is less steep. And then we just do this for each of them. It's literally just plugging in the points into this equation, getting its slope, then we're going to draw a line segment with that approximation of a slope. One of the things that I'm doing is I'm looking for another point to kind of aim for, as opposed to just fully eyeballing it. But that's part of the strategy. But it's just finding all these different numbers. So let's see, x is 1, y is negative 2. That'll be 1 over negative 2. That's negative 1/2. So I'd be aiming for this guy over here, because you go up 1 over 2. So I get there. And then negative 2, negative 3, negative 3/2. Then over on the other side, we have negative 2, negative 1/2, negative 3, negative 3/2. The other way. All right, so we get our little slope field here. From here, it may ask you to sketch it. We'll be sketching them in a second. Um, this one looks kind of like it would be a hyperbola, which is fun. Um, and then find the equation of it. Finding the equation, the solution, the general solution is what we just did. So here we could separate the variables. In this case, we'd multiply y over. This is more practice of what we were just doing. That's why we're doing this. So we'll have y dy equals x dx. We can take the antiderivatives of both sides now. So we get 1/2 y squared equals 1/2 x squared plus c. Can multiply by 2. We don't want 1/2 y squared probably. So multiply by 2, we'd get y squared equals x squared. Then plus 2 times unknown constant, still an unknown constant. We don't know what that number is. And then we could square root to get y equals plus or minus the square root of x squared plus c. But as I noticed that it looked kind of like a hyperbola. And so a hyperbola, we're going to keep the x squared and y squared. We're going to subtract it over so it's on the other side. So we'd have y squared minus x squared equals c. And then a hyperbola is generally going to be equal to 1. So we would divide by c to get y squared over c minus x squared over c equals 1. And then what that c value is would depend on whatever the initial condition is to tell us where we would be drawing this. We don't have an initial condition in this case, so we would just find the general form. Another one, we can make a slope field for x minus y. We won't find a general solution for this because if you notice, this is not separable. There's no way to get all the y's on one side and all the x's on the other. You might think, well, I can just add y and multiply by dx. Remember, you would have to distribute that dx. You'd end up with a y dx, and you can't get rid of that. So we won't find the general solution, but we can still make a slope field, x minus y. When they are equal, the slope will be 0. So when they're both 0, when they're both 1, when they're both 2, there and there. If x is 1 more than y, so like when x is 2, y is 1, the slope's going to be 1. So we have 1, 1, 1, 1, 1. That's when x is 1 more than y. When y is 1 more than x, so say at 0, 1 or 1, 2, that'd be 1 minus 2 is negative 1. So this line is going to be negative 1. Notice in that line, y is always 1 more than x. We can do, and we're going to have diagonal lines here. So once we find 1, it'll be easy. So here we'll have x is 2, y is 0. So that's going to be a slope of 2, which means everything in that diagonal is going to have a slope of 2. Then we'll have a slope of 3, a slope of 4. It gets pretty much vertical, slope of 5. And then on the other side, we'll have a slope of negative 2, slope of negative 3, slope of negative 4, and negative 5. And so here, we aren't quite to drawing yet, but we can see the path this is coming, or this is taking. It's going kind of in those directions. So we'll see what they look like in a minute. But this one we would not be able to find the equation for. Another one, this one's one of my favorites. It's dy over dx equals y over x. And so we can make the slope field. So here, when y equals 0, it'll be horizontal. And when x equals 0, it'll be vertical. And then when they're equal, it'll be 1. Or -1. And then when x equals 2, y equals 1, we have the 1/2. So we can use the origin as a base. Then same thing when they're both negative, or -1/2, 1/2. When x equals 1 and y equals 2, we get 2. So we can, again, use the origin. And what you'll find is that you can actually use the origin for all of these, because dy over dx equals y over x. That is just a slope. And so I like this because it's a starburst, like it's just kind of coming out at you. It also looks like you might be flying through hyperspace. So it's just kind of fun. So what would give us this kind of graph? Well, let's solve this one. It's separable. We can divide by y, multiply by dx. So we'd end up with 1 over y dy equals 1 over x dx. Antiderivatives means we'll have natural log y equals natural log x plus c. We can go e to the power. So we'll get y equals the e to the ln x plus e to the c. We're still going to have that constant times e to the natural log x is just x. This is y equals some number times x. It's a line going through the point 0, 0, which if you look at this, they all go through the point 0, 0, and they're just straight lines. So it just makes a fun slope field. But this is the differential equation for a line that goes through the point 0, 0. It's just the slope, because the derivative of a line that goes through the point 0, 0 is just the slope. So that's making slope fields. Next, matching. A lot of what we'll be doing is matching. It will be given some slope fields, will be given some differential equations, and we need to figure out which one goes with which one. There's a bit of an art, a bit of strategy to this. We're going to see some things that I look at when I'm doing this, but really it's going to be experience, practice, and you develop a lot of your own strategy for this. So when I'm looking at them, I start by looking at the equations. In the first equation, what I see is the 1 plus y squared. There is no x value, which means it does not matter what x equals, it's going to have the same slope for that y value straight across. That's going to make horizontal lines of the same slope. If it was backwards, if there was x but no y, we'd have vertical lines of the same slope. So now looking at the graphs, is there one that we can see that has a bunch of horizontal lines of the same slope? And it's all going to be positive as well, because 1 plus y squared is always positive. So that's another thing to look at. So if we're looking at number 2, notice each of these lines has the same slope all the way across, and they're also always positive. So I would say that that is number 2. Cosine of x plus y. Well, we know what cosine does. It makes waves, but when you have the x plus y in there, that's going to get a little bit weird. For instance, when x equals negative y, so on that negative diagonal, it's always going to be 0. Cosine of 0 is 1. So that negative diagonal is going to have to be 1. That one's a little bit weird. We can use process of elimination to help us out as well. If we go to C, it's x times y. I'd be looking for positives, negatives, and zeros. When either of them is 0, it's going to be 0. So it should be 0 along both axes. And then when they have the same sign, it'll be positive. When they have opposite signs, it'll be negative. So quadrants 1 and 3, we should have a bunch of positive slopes. Quadrants 2 and 4, we should have a bunch of negative slopes with zeros on both axes. Which one does that happen? Well, I see some negative slopes right here in quadrant 1, so that's not going to be it. Looking over here, we have, at number 3, we have a lot of zero slopes along both axes. Positives, positives, negatives, negatives. That matches what should happen when we're multiplying x and y. So that would be 3, leaving 1 here. I would still look to make sure. So we said when it's going to be a 1 slope on that negative diagonal. So we look at that negative diagonal. Do all of those look like they have about slope of 1? They sure do. And then negative 1s when it would equal pi, which would be about 3, or negative pi. So we can see that in there too, but that one's a bit tougher to see. And it doesn't behave like cosine would normally behave because of the x plus y on the inside. The b is not separable. We would not be able to separate out the x and the y there. A is. If we wanted to separate something that looked like that, we would divide by the whole 1 plus y squared. So we'd have 1 over 1 plus y squared dy equals dx, and we could take the antiderivative of both sides. The 1 plus y squared is going to give us an inverse trig function, so that's always fun. We're not going to do that here, but that's what would happen. So that was matching slope fields with the differential equations. Sometimes we'll be matching slope field with the general solution as well. This is a slightly different skill. So with the differential equation, we were looking at what would make those slopes. For the general equation, we're looking at the shape of the graph that it makes. So in this one, every graph we make looks like it's going to kind of come like that. What kind of thing makes a shape like that? Quadratic makes a shape similar to that. But then we have some things to match, so we can see what these look like. So y equals x cubed. The graph of y equals x cubed is going to look like that. Not quite. This one doesn't curve down as it goes to the left, it curves back up. It's going to be an even power, most likely. There are other things that could happen here, but I know I'd be looking at y equals x to the fourth. It's kind of what it looks like. When the powers go up, it gets a little bit flatter. So notice like it's a little bit flatter coming through 0 than a parabola would be. But let's finish looking at those. Natural log of x is going to give us a graph that looks kind of like that. Well, that's definitely not it. X plus 1 over x. 1 over x gives us a graph that looks like this. Adding x to it, I can't imagine that it's going to magically turn into quadratic shapes. In fact, it usually just, it's the same shape, it just gets stretched a bit. Y equals cosine of x. It's going to be in that general shape, which is not what this graph is, which leaves y equals x to the fourth as our general solution to this graph. So again, notice this is different from the previous problem. The previous problem, we were looking at each of the little tick marks, each of the little slopes. Here we're looking at the shape. We're not looking at the little slope marks. So that's matching it to the solution to the differential equation. And then finally, let's look at drawing a particular solution. So a lot of times it'll give us our differential equation. It's y plus 1 times 2 minus y over 2, which is separable. By the way, we're not going to, because this one in particular would be pretty gross, but we could find the general solution to this. But it gives us a slope field, looks kind of like this, and then it'll give us a couple initial conditions. It'll say y of 0 equals 2, and y of 0 equals negative 2. So for y of 0 equals 2, we just start out at 0, 2, which the tick marks here don't really work out too much because that's 2.5. 2 is going to be right about there. And then we're going to draw the solution from here. We're going to follow the lines. We're going to go where they tell us. We don't want to be crossing the lines because that means we're going at different angles, different slopes than what it's telling us. So just kind of go with the flow. This is telling us to go right this way, and then we can see an asymptote there. And then going back the other way, looks like that. And this is a bit of an art form. There are some methods. There's Euler's method, which you take the slope and you figure out what the point is just a little bit over. And then you find the slope of that point and figure out what the point is just a little bit over. And you can actually calculate it. And you can get the calculator to draw that out too with a program. It has its limitations, but that's a way of being more mathematical about it. Most of what we'll be doing, it's going to be more of an artistic rendering. You will get better with time, but it's probably not going to be perfect. So this other one though, x equals 0, y equals negative 2, is going to put us down here. So here we're going to go up towards that same asymptote there. And then this one's going down. So notice where we start gives us a vastly different general equation here. And so that is these two sections. Skylar, I hope you enjoyed that. We'll get to the next section, which is not on this topic actually. It's different topics next week. But until then, keep working problems, keep asking questions, and as always, happy mathing.